Alright, Internet, welcome back. So today we're going to do Leviathan 2, dose. And we're only going to focus on Leviathan 2 because this one is quite a bit more difficult than the first two. And when looking at other people's answers as they go throughout the Leviathan challenges, this one seems to be the one that lasts the longest and takes the longest for them to solve. So this may be the most difficult, but we'll find out. So first things first, we got into Leviathan 2, so what do we see? And also, preface all this stuff with, I had to cheat. I'm sure you'll have to cheat a bit. That's why you're kind of here right now. But I want to kind of walk you through some of the learnings that I've had through cheating a little bit and understanding more about this challenge and why it's exploitable and the weaknesses and potentially how to fix those weaknesses. Okay, preface out of the way, Leviathan 2. So if we do ls, we're going to see there's another executable file similar to the previous challenge. And when we look at this, this executable, very similar to the previous challenge, where we have a level we're trying to get to. So this is the user that owns the file, and this is us as the group user. So we're group, they're owner. And here you can see the owner actually has, yet again, set the sticky bit, which is similar to the last one. And basically what that means is that if we execute this file correctly, that means that we're going to have temporary access. So I did a bit of Googling on this, and when we look at ltrace, which I'll show you in a second, is that something we're going to use, there's going to be this thing called setting the effective, it's the effective UID. And the effective UID is basically allowing us to have effective permissions to run this file based off of what's said inside of it. So with all that being said, let's run ltrace first, just to see what happens here, and that was the first step I took, right? Because from the last challenge it worked, so why not let it work this time? So if we run it here, we can see that some stuff comes out that's semi-useful to kind of get us one step closer to solving the challenge. So first things first, when we come here, we can see that it's asking for a put, so it's looking for, it looks like a file, and it states that it's printing out something. So the printout is the usage, and it has a file name. This is the executable that we did, usage. So here you can see that the usage is our command, right? So we execute the print file, and it looks like it's looking for a file name. So it's called print file, so it probably has to print a file. So if we try to touch a file inside of here, so we do touch test, so create a file, it doesn't allow us because we're inside of a directory that we have no permissions inside of. So with that being said, I had to do a bit of searching around, and I came across the concept of using temporary directories. So I don't know if I have it listed here, but maybe in my notes. Let's see if I have anything in here useful. Yep, here we go. So let's jump back to our terminal and look at this note here. So you can see I noted out basically that the temp directory is a directory that people tend to use when doing these types of challenges, mainly due to the fact that in most operating systems, the temporary directory has this thing labeled the sticky bit. So I wonder if we can actually list that out. So if we do ls, here we go, we can see it. So if we look here, down at the bottom, we have our temp directory, right? This temp directory has this thing called the sticky bit. So is it sticky bit? Yeah, it's called the sticky bit. And the concept of the sticky bit is basically stating that everybody within the whole operating system, all the users, have the ability to create files and also delete files that they own inside of the temporary directory. Another interesting thing about the temp directory is that I noticed when playing around with this challenge that there's actually a cron job in the background, and that cron job is reoccurringly basically removing and deleting files from that temp directory to do kind of like some sort of spring cleaning on a consistent basis. And here it seems like that cron job is set up to do that quite often and quite frequently, because I actually got caught a few times where I was trying to solve this challenge looking at other people's answers where all my stuff got deleted, so I had to restart from scratch. So that's another interesting thing, is that when doing this challenge and doing other challenges, there's potentially an opportunity to have like a workaround where if you need to leverage a file or do something with creating or deleting something within a folder or a directory, you can do that sometimes within the temp directory if the sticky bit is set. And there is a website here. I'll quickly show it to you. So this one here had some interesting insights, and I may have already had it open here. I did. I'll add to you. So yeah, this website here basically walks you through what the sticky bit is and how it's used and how it can be manipulated from time to time. I don't think there's anything in here specifically that jumped out, but it was a useful article to read. So that's one thing to point out, is that within our challenge here, now we know we can create and manipulate files within the temp directory. Then we could potentially leverage those files then to print and see what happens with our file. So let's do that. So let's cd into temp, and we're going to have to make a directory in here. So let's make a directory, say, let's call it break, and we'll cd into break. Oh no, autocomplete, fine. So in here we have nothing, but let's create a file. We'll call it test, and we have our file here. So let's echo hello there. We'll echo that into test. And then what we're going to do is we're going to cd back into our home directory. So we'll cd back into home, and I think it was 2. Yeah. So now we're going to leverage this command, so we're going to execute it, but we're going to execute it specifically on the directory and the file we just created. And we can see when we do that, it allows us to actually print what's happening. Because we own the file, we have the permissions to do that, so we're allowed to do it. And remember, in our previous ltrace that we did, it told us that we weren't allowed to do it because we didn't have the permissions to do anything inside of that folder. But we do have permissions inside of the temp because of the sticky bit. So, with all that being said, now let's run ltrace here and see what happens when we print a file that we actually have the ability to do so. It gives us a lot of insight here into next steps of how we can execute and kind of exploit this and get this flag from this challenge. So first things first, we can see that it's running through some stuff. This is already there from the main C program that's written. But here's an interesting thing here. So we're running the access syscall. So the access syscall is something else I had to search. So if we jump back here, not cat, access here. So when looking at the access man page, you can see basically what they're doing is they're checking the permissions. So if we come down here, basically it checks whether the calling process can access the file, path name is a symbolic link, blah, blah, blah. So basically it's a check to say, does this person have access to do what they want to do with this file specifically? And if we come back here, we can see that now that we have access and basically file permissions inside of the temp directory here where it's checking, it knows that we have access to it. So it sets this the value to 0, meaning that we have access, and that's a true, so you can keep going in the program, keep following. So as we keep following through here, we can see that they're running a printf statement. That printf statement is basically calling cat, so it's going to cat out whatever we give it, which is another thing to keep in mind. So it's going to cat that out, and it jumps into this temp directory that we have permissions in, and we keep going a bit. So you can see that this printf is basically calling cat. It's going to call it on this this string that we're putting into it, and that string we're going to put into it is this item here, which is our test file. So once we've gone through those steps, you can see that it's getting our effective UID at the moment, right? So our effective UID at the moment is this ID, which has very little permissions. That's the one that's tagged against I think Leviathan 1 at the moment. That's what we are, and that's for both of these. But when you look at this, so it's gotten our effective UID, which is and this is another important piece, is that there's a difference between your UID. So your UID is basically the thing that you own at all times. So that is what's attached to your username, or kind of your name within the operating system. And then the other thing is actually your effective UID. And the effective UID is basically you're effectively adopting this user's identification while executing this process. So when executing this process, specifically this print file, we're temporarily effectively taking the permissions of the owner. Because remember, let's jump back for a second. Remember how I mentioned that works. Remember how I mentioned here where this one has a sticky bit, remember? So this is associated to the effective ID. So now that my effective ID has turned into Leviathan 3, the user, so I have temporary root access because of this I don't know if it's a sticky bit, this S bit, whatever this is. Now that this is set, that gives us the opportunity to have this temporary effective ID of 0. That's what 0 stands for. 0 is root. So we have that bit, and we can see that. So now that we've done this, we can see that it's okay, it's executed, you're all good, so you can move to the next step in the program. The next step in the program is to run the system call. So in previous challenges that I think I did with Bandit, or whichever one was the web one, is in over the wire, the system call is specifically doing a system command. So that's what the system call stands for. And I did a bit of Googling again just to remind myself of that. So we've looked at access. We'll go to that in a second. code. Go to that in a second. Where is this? All right, command injection. So this is leading to the point that I wanted to make. But inside of this blog post, which is pretty good, you should check it out, Imprava. And in here they're talking about the system call and how the system call can be manipulated in the sense that what it's taking is user input, and that user input is then turning into a system command. So if we jump back here, we can see that our user input is coming into the system command. So our user input is going to be the file that we want them to print out. You can see it's being catted, and that cat file is going to be that cat command is going to basically print out this string. So now that we know all this information, we kind of have an idea of what's happening in the background. We can begin to kind of manipulate this and see how we can actually leverage it for our own benefit to get the flag. So as I mentioned, the system call is happening, so that means we can incorporate more commands inside of that system call in addition to just cat. So that's one thing to kind of keep in mind. The next thing to keep in mind here is with the cat command, it specifically states that it's concatenating files and printing out the standard output. So with cat, you can actually print multiple things, right? So if we can print multiple things, and the specific program we're putting it into, the print file program, is checking if we have permissions for the first file, that means that if we can actually trick them, and let me get something dark so I can explain this better. Let's do it here. So if our program is checking, so we have cat, right? So we have cat here, and we can have multiple files. So we have file 1, file 2, file 3, file 4, right? So if our program's going through this cat statement and saying, okay, you have permissions to print file 1, because let's say file 1 sits inside of /temp. So we'll say file 1 is a /temp, right? So we have files to do this. But as the program continues and it approves this one, it'll actually go to the others without actually checking the permissions. And this is considered a race conditioning exploit, basically. So as you go through this, it's going to the next one here, and it says it's not checking the permissions because it's already checked the permissions here, so it's just going to execute now. So it's going to execute all these files and do as we please based off of how the program's set up. So the cat command is important to understand as well, because we can concatenate things together. All right, so now that we have all that out of the way, we have an idea of what's happening in the program. I'm going to then I'm going to walk you through 2 different solutions. So I actually found 3 different solutions here. So Derek Rook, he's on YouTube, he has a good approach. It's kind of convoluted and hard for me to explain, so I'm just going to explain John Hammond and CryptoCat's approach, which are both different, which is interesting because it shows you that you can approach a problem in multiple ways and hack a solution to get your flag. So let's start with John Hammond. So John Hammond uses a code injection, right? And I have his YouTube video right here, so you can always check that out if you'd like. And his code injection is leveraging this concept of putting together multiple items to then create a command within the system profile. And our specific attack we're going to do is actually using the semicolon here. So you can see on the command injection page on Wikipedia, there's a table, and we've seen this table in previous challenges. So let's go back up here. And in this table, it's basically showing you that you can actually link multiple items together. And when linking these multiple items together, you can actually chain commands. And when you chain a command, the command continues when it falls into the system call that we talked about earlier. And specifically, as I mentioned, we're going to use this semicolon here. We're basically going to concatenate two items together, or kind of sequence 2 commands together. So that's that. So let's run that command injection here, and then I'll show you the other attack. So let's go back into our temp directory, which may have been already deleted. Oh, see, I get to show you guys this. So if I try to cd into break no longer exists, and that is because of the cron job I told you about previously. So we talked too much, and the cron job came in and did the spring cleaning and ruined our temp folder, so we have to start over again. So with that being said, let's start over. So we're going to make the directory again. So we have our directory, we want to cd into that directory, and then we have no files. So now what we're going to do is we're actually going to create a file, but that file is going to have some special characteristics. So we'll say fake bash, and I'm going to explain what we're looking at here. So when looking at this, we can see that we're putting single quotes here. And the reason we're putting single quotes is because when you when you do something within cat, if you put single quotes around it, then it takes it as a literal. So it's going to take exactly what it sees, and it's not going to take anything else. So it's going to take all of what's inside of that. So what we're doing is we're putting in two things. So we're putting in fake, which is anything, any file. It could say hello world, it could say purple pickles, whatever you want it to. But then we have this semicolon. The semicolon is then going to connect those two commands together, so they're both going to be run when they run through the cat command in our system call that I talked about in the previous piece. And then that when it concatenates those two together, then it's going to actually call bash, which is going to give us shell. And that shell is going to be sitting within, hopefully, Leviathan 3, which then gives us our answer and our flag. So let's try this out. We've touched this file, and we ls it out. We can see it's a single file, and it's all smashed together. So now, if we go back to Leviathan 2, and we run our print file, we're going to run on temp, break, and then now we're going to run it on our fake file. So if we do this, it looks like it broke, and it looks like it didn't work, but in all reality it did. So it says no such file on your directory, basically stating that, you know, this doesn't exist, you can't do that. Reason being is that it only read this fake piece here. So fake doesn't exist inside of our temp directory, remember? We only have this file here. But even though this doesn't exist, it's still going to continue executing the program because we added the semicolon there. So since we have the semicolon there, then it's going to create a bash script, and as you can see, that we're at Leviathan 3, we're no longer at Leviathan 2 here. So now, if we come into our password, our handy dandy password file, we can cat out our password for the next level. So now we have Leviathan 3's password. So then we can go to that one. All right, so that is the first attack, right? So now we're going to do another attack, which is super interesting. So this is command injection. We finished that one. So the next one is actually a toctao. A toctao. So a toctao is a time of check to time of use. That's the type of attack that we're looking at. And now, interestingly enough, this attack is used quite often, and it's still pretty prevalent in many different systems. It just manifests in different ways. So the way that this is going to happen, and the way this attack is basically affected, is what we're doing is it's as exactly what it states. You just kind of have to really think it through. And I've read a lot of different documents to understand this. But first, let's give cred where credit's due. CryptoCat is the one that taught me how to do this for this challenge, and I kind of listened to what he said, and then I did a bunch of research outside of that. So definitely check that out from him. And when looking at this, so let's walk this through. So a time to check to time of use. Within our program, and let's actually take a step back here. This actually might be useful if we, let's see, ls. So I wonder, I'll trace. Let me actually, I want to walk you through specifically what it looks like. So break. All right, so let's touch a file and call it test, and we'll echo hello into test. Test, not tech. All right, so the reason I'm doing all this is because I want to show you specifically what I'm referring to. So temp, break, test. Okay, cool, that works. So now we want to ltrace it so I can explain this. All right, so the thing I want to explain is that this program currently is going through a series of steps, right? So we're walking through this program, and it's basically working its way down this program and executing certain steps. And as it executes these steps, there's two really important things that happen with our time of check and time of use. So our time of check is occurring here, which is sitting at the access systems call. And this access system call is basically stating, do you have access to this directory and access to this file to execute it? If yes, continue. That's our check. And here we can see it's 0 because we do have access to that system, so we can do as we please and we can continue. Now it's done that, so it's going to actually change, remember, our effective user ID to root, so we can do as we please and do basically whatever we want. And then the system call here is the time of use. So this is check, and this down here is use. So we have our time of check and we have our time of use. And in the use, it's going to basically print out hello because that's what I've asked it to do. But with that being said, we can do other stuff. Instead of just doing hello, we can actually maybe do something more malicious. And the specific malicious attack that they decided to do here with this specific situation is creating a symbolic link. So a symbolic link is basically a soft link between one folder location to another folder location. So let's set this up, and then I'll explain it in a second. So we'll go back into break. Oh, it disappeared again. You see that, guys? See that? Guys and girls? It's gone. All right, cron job screwed us over. So we're going to create another one called break, and we're going to cd into break. Maybe. Break. Can't spell break, sorry. All right, so we're going to create two things. First, we're going to create a symbolic link between a fake file. So to create a symbolic link, we're going to do ln for link, and we're going to do s for symbolic. And then the symbolic link is going to actually be between the location we want the password, which we know is in Leviathan pass, Leviathan 3. And then our symbolic link is actually going to be connected to our location that we have access to, and we can just call it test. So to check that we've created this correctly, we can come in here and we can see that within the thing that we just created, we have a symbolic link between test. So we can see that this is basically read, write, execute for everything. We're root, we can do whatever we want. And that's linked to the Leviathan 3 folder here where we know our password is, and that's what we want to get access to. So we have this set up. So the next thing is actually creating another file. And this other file is going to be named very similar, but with a slight tweak. So the slight tweak we're making here is that we have test, right, which has our symbolic link that we want, and we have test2. So test2 is remember we have quotes around it, so it's taking it as a literal of test2, but there's a space here, right? And with that space, that's going to be a big thing in our favor. And the reason being is that what the program is going to do is it's going to first check test, and if it sees test and test equals approval, then it's going to continue, and it's going to execute that symbolic link. So let me kind of run this and show you what's going on. So yeah, before I run out of time. So let's go back to 2, and we're going to print file, and that print file is going to happen on our break, and it's going to happen on, I think, test2. Test. Why did I do that? All right, 1 second. Let's try this first. Okay, no, that's wrong. Test2. There it is. Gotcha. All right. So, as I mentioned previously, we're doing a race condition, and the race condition is occurring between multiple files. So what's happening here, and I wonder if I can actually L-trace this. Yeah, nice. All right, so what's happening here is we're doing our access check, right? So we're doing our test here, and you can see that it's checking to see if we have access to run test2. So when it does that, it says, yes, you have access to run test2, you have root user level privileges. So we are 0 because we have access. Next is we're going to run through the printf, it's going to say what you're printing. And then down here you can see it set our effective UID to root 0 again, and now we're going to actually execute this piece here. So when we go to execute this, it's going to cat out test2 under here, but in addition to that, it's going to actually symbolically link test, and it's going to cat that out as well, because you can see this is attached here saying bin cat test. And the reason being is that the race condition is occurring where basically it's going through and it sees test, and once it sees test, then it executes, because it knows that we have access to that file, and it knows that there's another file inside of the directory called test. Because what it's going to do is it's going to see this file here first before it sees this one, because this one has an additional space and then a character. So once it sees this one first, it's going to execute this. And when it executes that, as I said previously, it's going to go to our symbolically linked password folder and file, and it's going to then give us our password, which is right here. So that is the time to check and time to use attack, and that's another privilege escalation attack. So these are both privilege escalations. So command injection and this one here. And here you can see I was just looking at some of the weakness enumerations, and they talk you through the attack, what it is, and then also they specifically call the attack that we just did, it's called a race condition enabling link following. So it's following a link basically once you've beat the race condition. And then, yeah. So that was Leviathan 2. This video is probably a lot longer than it could have been, but I hope that explanation was semi-useful and comprehensible. And I'll see you on the next one.